Hello everyone, ladies and gentlemen. Welcome to my channel. Again, we have another video that is indeed this continuation of the previous one. In the previous video, we have solved one-dimensional Poisson equation using finite element method. But in that video, we have used linear shape function. In this video, we will see how we can increase the accuracy of solution without increasing the number of mesh just by including quadratic shape function instead of linear shape function. Yeah, but before starting the video, I have a couple of announcements for you. First, I have created a Telegram channel and I answer to your question in that channel because some of your question is really hard to be answered in the YouTube comments. I create this channel and I upload the answer in the format of PDF or JPEG in that Telegram channel. The link is in the description of my YouTube channel. I think you will find this channel useful. And second thing is that all of these contents are free, but if you think you find some value in this content and you would like to help my channel and support my channel, I included my crypto wallet address in description of YouTube channel. Your help indeed enable me and encourage me to creating more content like this. So without any further discussion, let's dive into the theory. Okay, let's start and let me choose this laser pointer. And as I mentioned, the title of this video today is employing finite element method using quadratic shape function, and as a case study we will solve a one-dimensional Poisson equation. In the previous video we saw that we need indeed to discretize our domain into some mesh, and indeed the numerical solution is some approximation of this, let's say, exact solution. Imagine that this blue line is exact solution. We discretize all of domain into only one mesh, that the nodes of this mesh is at the x1e and x2e, and we solve indeed we find the numerical solution, and we saw that this numerical solution is approximation of analytical solution. But in that video, we employed some linear shape function. That the linear shape function was following that it might be 1 at the position of one of the nodes and 0 at the position of another node. And also we had another shape function with the vice versa condition, means that this shape function is only 1 at the position of node 2 and it is 0 at the position of node 1, and this numerical solution will be in the superposition of this shape function psi1 and psi2 with some coefficient v1 and v2 that indeed is our desired solution. What if we add some extra node inside this element? In this case we can see that, okay, if we somehow find the solution, the numerical solution, not only at this point and at this point, also at this point, easily we can see that this numerical solution is better approximation of let's say exact solution if we compare it with let's say with this type of solution. But what about shape functions? We say that, okay, in the linear shape function, this shape function is 1 here and it is 0 here. Similarly, we can conclude that this shape function also should be only 1 at the position of node number 1, and it should be 0 at all the other nodes. As you see here, at this node and this node, the value of this shape function is 0. Similar condition for shape function 2. You see that this is only 1 at this node, and at all the other nodes it is 0, and it is easy to see that the third shape function should be 1 only at the position of this node, and it should be 0 at the position of the other nodes. And you see that here we have indeed some quadratic function, and in this case if we add some extra point inside this element, in this case the numerical solution should be superposition of this 3 shape function with the coefficient of v1, v2 and v3. Just I want to, let's say, swap this index of this node and this node. Here it is v1, v2, v3. Let's define following. Let it be v1, v2, v3, and let it be x1, x2, x3, and this shape function, let it be psi1, this one psi2, and this y psi3, just for convenient. Okay. What about this extra point? We say we need to add to this mesh to further increase the accuracy of the numerical solution. This point indeed should be lies inside mesh, and I think the most convenient point for this point is to be at the middle of node number 1 and node number 3. Yeah. Therefore, x2, the position of x2 should be x1 plus x3 divided by 2. And in this case, in the previous video, we discussed that it's better to define some non-dimensionalized coordinate zeta. And in this case, the definition of the zeta should be following. It means that the zeta should be connected to the x by 2x minus x2 divided by x3 minus x1. That indeed, this x3 minus x1 is the delta x of our mesh. And if we substitute x1 in this zeta, simply, you see, we will get minus 1 for the zeta. And if we substitute x2 in this function, we will get obviously 0 for the zeta. And if we substitute x3 instead of x here, we will get 1 for the zeta. It means that we discussed in detail why we need to to change the coordinate. Therefore, I recommend you to first watch that video. You can find the link exactly here. Okay, and you see that this is the representation. If we have any arbitrary node, any arbitrary mesh inside the domain, we have 3 quadratic shape functions like this, and in new coordinate of zeta, the appearance of the shape function is like this, and zeta will be minus 1 or 0 or 1 when x takes x1, x2, x3 respectively. And if we look at the appearance of this psi1 function, we can see that this psi1 function has two roots. The first root is lies on the position of 0, and the second root is at the position of zeta equal to the 1. Therefore, we can imagine that this psi1 should have such a format: c zeta times 2 zeta minus 1, because when we put zeta 0 here, it will be 0. Also, if we put 1 here instead of zeta, again psi1 will be 0. But what about this coefficient c? We say that, okay, this function psi1 is 1 here, psi1 is 0 here, and psi1 again is 0 here. Therefore, we use this, let's say, boundary condition. If we put minus 1 instead of zeta, therefore this function is 1, c times to the minus 1 minus minus 1. You can easily see that the value of this coefficient c should be 1 over 2. Therefore, this is the, let's say, mathematical representation of the first quadratic shape function. Let's keep it. And again, we know that psi2, this green shape function, is only 1 at the 0, and it is 0 at the position of minus 1 and plus 1. Therefore, we use this condition. And okay, before that, we can see that this function have two roots, one at minus 1, the other at plus 1. Therefore, we can conclude the general form of psi2 should be like c times 2 1 plus zeta times 2 minus 1 minus zeta. And you can easily see that there is two roots, one at zeta equal to the 1, and the other root is at zeta equal to the minus 1. And if we use this condition here, simply we get 1 for the coefficient of c1. For this is the, let's say, second shape function in this new coordinate. And about the third shape function, we will use the same approach. Substitute this here, and we will see that the coefficient also should be 1 over 2, and the third shape function should be 1 over 2 zeta times 2 zeta plus 1, because one root is, for the shape function, one root is at the position of 0 and the another roots is at the position of -1. We have all of the shape functions, and we say that the relation between the old coordinate and this new non-dimensionalized coordinate zeta is following. You may ask how you calculate this, how do you find this relation between zeta and x? The answer is simple. Look, we say that this numerical solution indeed is such a superposition of psi1, psi2, and psi3 with the coefficient of v1, v2, and v3. It means that if we multiply this coefficient to the psi1, this coefficient to the psi2, and this coefficient to the psi3, it will give us this numerical solution. Yeah? Intuitively, we can conclude that if we multiply this x1 to this psi1 function and x2 to this psi2 function and x3 to this x3 function, it should give us the this x-axis, yeah. But this time, if we use the this shape function at the x-coordinate, it will be nothing interesting. But if we use psi1 at new coordinate, we will derive the same equation that I showed you. How? Okay, let's just substitute psi1 in new coordinate and psi2 and psi3 in this equation. As you see, psi1 is 1 over 2 zeta times 2 zeta minus 1, psi2 is this one, and psi3 is this one. Let's move further. What we have a common factor of zeta here and here. Let's write these terms here and factor out this zeta. Therefore, what is left will be x1 times 2 1 over 2 zeta minus 1 and x3 times 2 1 over 2 zeta plus 1. Okay, and if I multiply this x1 and x2 into these terms and expand this term and keep this term, what I have x1 1 over 2 zeta minus x1 here, and I have x3 times 2 1 over 2 times 2 the zeta, another x3 here. Therefore, I have x3 minus x1 divided by 2. That comes from this multiplication and this multiplication. Okay, let's move further, and here, what do we have? Okay, here, if I multiply this zeta inside of this bracket, I have indeed x1 over 2 plus x3 over 12 zeta square, and this is the same term, and this is the same third term without any changing. And here you see that we have a common term of x1 plus x3 divided by 2. We factor out this common term. What is left will be zeta squared here, and this term that is written here, and I wrote this term here. The same equation from the previous slide, and we see that this multiplication will be indeed 1 minus zeta squared. Zeta squared will cancel this zeta squared, and it will remain only x1 plus x3 divided by 2, and here x3 minus x1 divided by 2 zeta. And we define this x1 plus x2 divided by 2 with x2. Yeah, indeed, this is the position of this new coordinate that is indeed at the middle of x1 and x3. Therefore, we have this simple equation. I bring this term to the left-hand side. We have x minus x2, same term. And by multiplying of the both hand side of this equation with a 2 and dividing both hand side with these terms, I will we will finally get to the relation between the non-dimensionalized coordinate zeta and the old coordinate x. And this is how we can derive indeed the relation between zeta and x just by using of the shape function that we defined. You remember in the previous video we start with this type of Poisson equation, yeah, and we define the vector d to be minus derivative of v over x, okay, and we saw that indeed this representation is the strong form of a PDE, and we saw that weak form of this PDE by defining of v like this should be like this, and we just integrated over one element when we derive the weak form of this equation. Then we just integrated both hand side of that equation over one of the element. In that case, when we had linear shape function, there was only two shape function here, but because here we have quadratic shape function, it must be three shape function. That's why we have three shape function here, and the integration boundary is from x1 to the x3, that is in the lower boundary of the mesh and the upper boundary of mesh. Now we know that, okay, we have three shape function, therefore we need to substitute all three shape function here, psi1, psi2 here and here, and psi3 here, here and here. Therefore we have a system of equation for one element. Yeah, but from the boundary condition of, let's say, boundary conditions of this element, we know that psi1 is 0 at the upper node, at the node of x1, but this is 1 at the lower node, that is x1. Okay, and psi2 at the position of x3 as x1 is 0, if you remember, and psi3 is 1 at this point, and psi3 is 0 at this point. Just by taking into account this condition, this will be our indeed system of equations, a bit simplified. Now all we need, let's just expand this sigma, and we will have psi1, v1 times 2 psi1 plus v2 times 2 psi2 plus v3 times 2 psi3. And if I use the extended form of this sigma, this will be the system of equation, my system of equation again. And you know that v1, v2, and v3 is some constant coefficient, therefore they can come out of derivative and out of integral. Yeah, and here I just first write the d psi 1 over dx first, then this expansion for all of these equations. Therefore, if I just multiply these terms to this, and also in all the other equations, it will be the format of my system of equations. Yeah, that's v1, v2, v3 is some unknown coefficient, constant unknown coefficient that we are interested for calculation of this coefficient. But let me define this integral with k11, this one with k12, this one with k13, 21, 22, 23, 31, 32, and 33. And let me define this integral with s1, this one with s2, and this one with s3, just for simplicity in the notation. Yeah. Therefore, this will be the format of my system of equation only for one element. Yeah, and I can easily write the matrix form multiplication of this for let's say this system of equation, and the matrix form of this system of equation easily should be like following: that aij indeed is the multiplication of derivative of psi I psi j and the integration over the elements. Yeah, and the s is multiplication of psi shape function to the f, that is in the right hand side of the Poisson equation, and here we assume that this is constant, and again integration from the lower boundary of the mesh up to upper boundary of the mesh. And we define the zeta similar to the previous video. Let's define this delta x for let's say the first element with he, or for any element we define this delta x with he. And from this we can see that this dx might be related to the d zeta with some coefficient of he over 2. And if I just use this dx here and write the d psi I and d psi j in neo coordinate, I will get to such a equation for kij and si. And in previous video I just discussed in detail how we can get this equation from this equation. You can refer to that one, but this is not very complicated, and I think you know it. Now we are interested for the calculation of this coefficient k, that is in the integration over the element in the non-dimensionalized zeta coordinate, and we know that in this non-dimensionalized zeta coordinate, zeta changes from -1 up to 1, as you see here. Therefore, let's calculate the derivative of this shape function, and you can, I think, easily calculate the derivative of this function will be zeta -1 over 2, derivative of this shape function will be -2 zeta, and derivative of shape function will be zeta plus 1 over 2. Therefore, all we need is just substitute this derivative in this equation and try to calculate this k factor. Yeah, for example, k11 will be -2 over h, integration from -1 up to 1, zeta -1 times 2 again zeta -1 times to d zeta, and this integral easily can be calculated, and if you calculate this integral it will be 7 over 6, and by multiplying out this to this coefficient it will be minus 7 over 3 he. In the same form you can show that k12 is 8 over 3h, k13 is minus 1 over 3h, k21 is similar to the k12 8 over 3h, k22 will be minus 16 over 3h, k23 similar to the k12 will be 8 over 3h, and k31, k32 and k33 will be such a value, because all of this is just the calculation of some simple integral, and if you calculate this integral by using all the derivative of this shape function you will get all of this coefficient. Great. Let's this time try to calculate the s coefficient, and s coefficient is multiplication of f and again this shape function, and for example s1 will be h over 2f comes out of the integral, and 1 over 2 zeta, zeta minus 1, that is indeed psi 1 times 2 d zeta, and again if you calculate this integral, that is very simple, it will be 1 over 3, therefore s1 will be h over 6 times 2 the f. In the same format you can easily show that s2 might be 2 times h over 3 times 2 f, and s3 might be h over 6 times f. Great. We calculated the k coefficient and we calculated the s coefficient. Therefore, matrix form of the system of equation only for one element will be like this. And this is what we want, because once we calculated such a matrix multiplication, we can easily calculate this unknown coefficient, that is value of the potential at node number 1, 2, 3 will be just inverse of this matrix times to the right hand side matrix. But let's move further, because we know that one element will be not enough accurate. Therefore, if we try to calculate this same system of equation for the another element, this is for one element, and if we try to calculate for other element, that is element number 1 and element number 2, for element number 2 we get the exact matrix form, and what is changed here, the only thing that is changed is that the delta x for the element number 1 and element number 2, maybe it can be different. If we use linear discretization it will be the same, but I'm deriving the theory part for general, let's say element, that in this general form of the elements, the delta x1, delta x2, delta x3, or h1, h2, h3 is different. Yeah. Therefore, the only thing that is different here is that for the element 1, this delta x is he. For element 2, this delta x is he1, and here is he2. Now, what we need, now this is time to connect these two elements to each other. Now we assume that we have two elements, therefore we need to connect these two elements to each other. But we know that the element number 1 at this node should be the same. Indeed, these elements are common in the node number 3 for the element 1 and node number 1 for the element 2. Yes. Therefore, I just define because okay, when we have two elements, yeah, how many nodes do we have? 3 for the first one and 3 for the second one, but they are common in one of the nodes. Therefore, in general, it should be 5 nodes for two elements. Yeah. Therefore, I define this the value of the potential. Instead of V1, E1, V2, E1, and V3, E1, I define it with V1, V2, V3, V4, and V5. Yeah, but we saw that for the element number 1, there is no dependence of the potential at the point of V4 and V5. It means that this column should be 0, and this column should be 0, because there is no dependence of the system of equation for the element 1 to the V4 and V5. Similarly, for the element 2, the system of equation in element 2 is just function of V3, V4, and V5. Therefore, there might be 0 row here and 0 columns here. Now, all we need to connect, let's say, or add this system of equation together. And this indeed, what you need is just add this element here, this here, this here, this here, so on and so forth. And you'll see that they are connected here. This element will be added to this element. And if you do this, this is indeed the system of equations in a matrix form, by assuming that we have two elements in our simulation domain. And when we have two elements, the number of nodes will be 5. Yeah, and if you notice, you can see that indeed these terms are related to the element number 1, and these terms are related to the element number 2. Yeah, and I think I forget to say that, okay, because here we have a term of d at the position of x3 of element 1 minus d at the position of x1 on element 2. This is indeed the difference of the d vector at the one element and at the second element at the common nodes. And if there is no surface charge, we know that this d1 minus this d minus this d should be 0. Okay, therefore this is for two element, and if we try to calculate this matrix multiplication by assuming 3 element, yeah, we will get such a matrix form of this let's say system of equation by assuming that we have 3 elements. When we have 3 elements, there might be 2 times 3 plus 1, 7 nodes, yeah, and these elements or these terms are related to the element 1, these terms are related to the element 2, and these terms are related to the element number 3. Yes, again we have system of equation by assuming that we have 3 elements. Now I think this is enough for theory part, that we can write or implement our code. But one thing is left, and that thing is that we know that if we want to have some unique solution for any PDE, we need to have some boundary conditions. Therefore, it means that the boundary conditions means that we know the value of the potential at the left boundary and at the right boundary. And the value of potential at the left boundary is V1, and the value of potential at the right boundary is V3. How do we can include the boundary condition? Following. Look, guys, what do we have here? You see that we have one equation, 2, 3, 4, 5, 6, 7. We have 7 nodes, 3 elements. Okay, we have 3 elements and 7 nodes. Okay, but we indeed each of these equations give us the unknown potential at the correspondence element, yeah, at the corresponding element, at the corresponding node. But because we know the value of potential at the first node and the last node, we do not need this equation, and also we do not need this equation. Therefore, the first thing is that we remove this line or this row and this row from this matrix, and this row and this row from this matrix, and this row and this row from the second matrix. Okay, I just first remove the first row. When I remove the first row, it will be like this. Yeah, because first row shows indeed give us a system of equation that calculate the potential at the V1, but we know the V1, we remove it. And if I remove the last row, that is in the equation that gives us the value of potential at the right boundary, and we do not need it because we know the value of the potential. Therefore, if I remove the last row in this matrix, what is left will be following. But again, we have here, look, we have this multiplication to this multiplication, that again is V1, and also this multiplication to this multiplication to this one. Again, we have this times 2 V1 and this times 2 again V1. We know the value of V1, therefore we send it to the right hand side. Therefore, this times to this goes to the right hand side, and this times to this again goes to the right hand side at this position. I just kept this matrix kept this matrix to just transfer this multiplication to the same matrix, because it is indeed survived from this matrix, but all of these element in this matrix is 0, but I put this matrix here to show that this multiplication should be comes here because when we send this multiplication to the right hand side, it should be comes to the right hand side of the first equation. Yeah, and because this is the second equation, and if we send this multiplication to the right hand side of the second equation, the right hand side of second equation is here. So if I do this, and you see that the sign might change because we send from left hand side to the right hand side, the sign should change, and here a 0 column is left, and again we see that this multiplication in the last equation times to the v7, and this multiplication in the equation before the last times to the v7 should comes again to the right hand side. If I send this multiplication to the right hand side, it will be here, and if I send this multiplication to the right hand side, it will be here. What we did, we just, instead of writing out the system of equation and looking at that v1 and v7 is known, we just send this multiplication to the right hand side of the equation in the matrix representation. You can write the system of equation. If you didn't get it, you can write the system of equations, and we know that for 7 nodes there is 5 equations, yeah, but in this 5 equation, if there is any v1 and if there is any v7, due to the boundary conditions, we know the value of v1 and v7. Therefore, all terms that contains v1 and v7 is sent to the right hand side of the system of equations. After that, if you write the matrix form of that system of equation, it should be like this, but we have 0 column here and 0 column here that we do not need anymore. Therefore, we remove this column and this column, and this is the final form of the matrix representation of the system of equations in using of a finite element method and quadratic shape function, and assuming that we have only 3 elements in our calculation. And as usual, because this matrix is known, it depends only on the delta x. This matrix is unknown, we define it with VC, and there is some right hand side matrix and another right hand side B. That this B stands for boundary condition, means that this right hand side matrix here comes from boundary conditions. As I mentioned, V1 and V7 is known due to the boundary conditions. And now all we need to calculate the inverse of this matrix and multiply it to the right hand side matrix. It will give us the V3. And here you see that we have 3 elements, element number 1, element number 2, and element number 3, and the simulation domain lies between 0 and some thickness of d. These are green because we know the value of the potential from the boundary condition, and these middle nodes indeed are the nodes that we added to each element for increasing the accuracy of the calculation. But as I mentioned, I assume that the discretization is not uniform. It means that we may have different delta x or h for the element number 1 and different h for element number 2 and different h for element number 3. That's why I just kept this h coefficient in this matrix and also here and here. So this is the theory part. I think all we need just to implement such a multiplication and try to calculate this VC. So let's go to the MATLAB and start implementation. Okay, this code that you see here is for the previous video that was Poisson equation using finite element and linear shape function. Let's just have a look. And you see that we had analytical solution with magenta and numerical solution with this cyan color. And here the number of indeed the elements was 100. Now I want to save this code to another file and add what we discussed in theory to this code. Okay. we do not need to change the analytical solution here. Therefore, we go down here. Okay, first of all, here n is number of elements. Now I change it to ne, number of elements, and let's start with number of elements 3. And we know that when the number of elements is 3, number of nodes should be 2 times number of elements plus 1. Okay, number of elements plus 1. E is the thickness of simulation, that is from 0 up to 12 and the power of 10 minus 6. And if f is some number, left the value of the potential at the left boundary and the value of potential at the right boundary. And this is the analytical solution. Now, when the number of element is 3, okay, let's start by changing this x. I want to define xe. xe indeed is the position of the nodes for the lower and upper boundary of each element. Therefore, I linearly discretize this domain or this interval from 0 up to d with the number of element plus 1. When the number of element is 3, number of x should 4. And okay, just let's go step by step. I disable all of these commands. Control R, and I want to see the value for the x. Therefore, press F5. And this is the number of x from 0 up to 0.5, from 0.4, from 0.4 up to 0.8, and from 0.8 up to 0.12. And we have 1 element, 2 element, and 3 element. Okay. Just by referring to these slides, we see that indeed xe represents this coordinate, this, and this coordinate. Therefore, he comes from the subtracting of this coordinate from this coordinate from this, and this coordinate from this. Therefore, in this case, he, okay, let's say x, should be xe from, let's say, 2 up to ne should be subtract, let's say, another xe from 1 to up to ne minus 1. What does it mean? It means that I subtract this from this, and this from this, and this from this. Just let's see if it's okay or not. For h is xe minus xe, which xe, x2 minus x1 up to xe ne up minus xe ne minus 1. Press F5. Okay. There's some mistake here. Why? Because you know that when the number of elements is 3, number of nodes is 1, 2, 3, 4. Therefore, number of he should be 1, 2, 3. But we have 2 h here. Therefore, it should be NEH. Size is from 1 up to 3. Now, let's just try it. There's something wrong. And say, okay, this one should be minus 1 minus NE. Now, okay, yes. What I did, I just did, look, we have xe coordinate, that is here, here, and here. And using this command, I subtract this from this and save to the he1. And I subtracted this from this and save to the he2. And I subtracted this from this and save to he3. Now it's okay. We have xe here and we have h here, but we have another coordinates. We have some coordinate at the middle of this, let's say, each element. Therefore, I define another xm. I'm defining xm. M stands for the middle. Let's first define the size of this xm. When the number of elements is 3, 1, 2, 3, therefore there should be 3 middle coordinate, 1, 2, 3. Therefore, the size of this xm should be, let's say, 1 column and 2 times n not 2 times NE, it should be NE, right? Because the number of elements is 3, therefore, similar to the H, XM should have 3 coordinates. See? Okay, this is 0, 0, 0. Okay, now, how we can determine the XM? We say that let's change. Say that for I from 1 up to length of, let's say, up to length of XM, yeah, XM, and I'm saying that give to the XMI what we are giving half of, let's say, XEI and XEI plus 1. Yeah, once we give this, let's say, average of neighboring node to the XM, it should give us XM, and let's check it, and it's true. How? You can easily see, because this is, okay, this is XE, right? That is at the coordinate of 0, 0 0.4, 0 0.8, and 12. And this plus this will be 0 0.4 divided by 2 will be 0 0.2. This plus this will be 10 divided by 2. This plus this will be 12 divided by 2 will be 0 0.6. And this plus this will be 20 divided by 2 will be, let's say, 0 0.1. Okay, and it's correct. Now we need to have information. I define some X vector contains all information of XE and XM. It means that because on the X coordinate, no matter where is this node, either at the middle of the element or at the boundary of the element. Now I want to define some X that contains information about all these nodes. Therefore, the size of X should be what? Zeros. Zeros when the number of elements is 3, therefore number of nodes on X coordinate is 7. It should be 1 and 2 times NE plus 1. Yes. Let's see, it should be 7. 1, 2, 3, 4, 5, 6, 7. Okay. And where does coordinate of X comes from? It comes from either XE, this, or either XM. Therefore, I define some loop, and I say that let's change I from 1 up to length of x n. Okay, and I say that, okay, because you see when I is 1, the coordinate for x comes from xe, right? But when I is 2, the coordinate from x should comes from xm. It means that all I'm trying to do is that I want to put this element here. The second one comes from this element here. Just let me disable this edge. We do not need to see this edge anymore. Okay. I want to see only xex. I want to see only xe, xm, and x. Again, I do not see x here. One more time. I'm trying is to put this one here, this one here, this one here, this one here, this here, this here, and this here. Therefore, depends on when the index for this element is even, it should comes from xe, and when the index of this array is when the index of this array is odd, it comes from xe, and when the index of this array is even, it should comes from xm. Therefore, let's define some parameter as the s. I'm saying that capital S. Let's define s to be minus 1 in the power of I. Minus 1 in the power of I. And I can say that, okay, if when the I is odd, the s will be minus 1. When the I is even, the s will be plus 1. Therefore, when s, parameter s, is minus 1, else n. Okay, I'm saying that when the s is minus 1, it means that I is odd, right? And xi should be replaced with xe with some j. But what is j? Okay, I'm defining some j here and say that let j be 1. Okay, and after that I'm adding 1 to the j to take into account the further, let's say, the further elements in the xe. You can easily see here when I is 1, s will be minus 1, and x1 comes from xe1. Yes, and xe1 is 0. x1 is this 0, is again 0 here. Therefore, it gives this xe here. But when s is not minus 1, s will be plus 1. I'm saying that if to the xi, for example, when I is 2, it gives to the x2 gives what? Gives from x middle, let's say jj. And what is jj? I'm defining 1 for the jj. When and defining 1 for the jj, when I is 2, it gives xm1 to the x2. After that, I'm saying, okay, add a 1 to the jj for considering upcoming index. And let's try if it's okay. We might finally see the x. Okay, I'm writing an x here and let's see. And you see that it's okay because this elements is 0 came from xe, right? And this element is 0, 2 came from xm. The second element is 0.4 came from xe, and the third one is this came from xm. The fourth one came from here, fifth one came from here, and the seventh one or last one again comes from xe. Therefore, by defining such a loop, we just assign xm and xe to the x coordinate that contain information, all information about the nodes. Okay, now after defining x, we need to define this matrix. Yeah, when the number of elements is 3, the number of nodes is 1, 2, 3, 4, 5, 6, 7. We see that the size of this matrix is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. It means that I'm defining some matrix S. Okay, I'm defining some matrix X S when the number of nodes that we defined here with n, number of nodes. Okay, here it's number of elements, yeah, and this one is number of nodes. Number of nodes. Okay, number of nodes is 7, therefore it should be n minus 2. Where is it? Yes, n minus 2 and n minus 2, and let's see if it works or not. Yes, we have created some 0 matrix that all elements are 0, and we need to one by one assign the elements of this matrix from what we see here. Okay. Therefore, let me enable this one. I'm saying that, okay, let's remove also this one, we do not need. I'm saying, okay, let's change I from 1 up to length of length of x. Okay, length of x. And what I'm seeing, I see that, okay, first of all, when the I is 1, the first element is minus 60 divided by something. But when I is 2, for example here at 2, 2, it is minus 7 divided by something, minus 7 divided by something. Again, when I is 3, at m3, 3 is minus 16, 4, 4 is minus 7, and 5, 5 also is minus 16. Again, I define same S parameter. I'm saying that when determine whether Si is even or odd by defining S to be minus 1 in the power of I. Okay, I'm removing this and removing this. And I'm saying that if S is minus 1, else, and okay, if S is minus 1, M, for example, 1, 1 should be minus 16 divided by H, again J, and here I'm giving J to be 1, okay? Otherwise, okay, it was minus 16 divided by 3H. 3 times 2H J. Okay, let's say otherwise do nothing and see if it's okay or not. Okay, I want to see updated. And you see that we assigned 1, 1, 3, 3, 1, 2, 3, 3, 5, 5, and 7, 7. Okay. What else? But if S is not minus 1, it should be 1. Therefore, in this case, give minus 7 divided by this one. Minus 7 divided by 3H1 divided by 3H1. Again, minus 7 divided by, say, 3H1. Control C, Control V. But once, notice that here in this element and this element we have HE here, HE1 here, HE1 here, and HE2 here. Therefore, this one should be HI plus 1. It means that when I is 2, it's minus 7 divided by H1 to the M22, also minus 7 divided by 3H2 to the M22. After that, we say that, okay, add one number to the J for considering the other H. And let's see, there is some error. And the index of number of the array element is 3 in this case. Okay, therefore, because the length of x, Control V, is 7, but size of the matrix is 5, therefore it should be minus 2. Now it should work. And you see that we assign all this element on the main diagonal of the matrix according to this loop. But also we have another element here and another element here. For example, when I is 1, we say that M1 and 1 plus 1 should be 8 divided by 3 times H J. Yes. In addition, another M, that is I plus 1 and 1, should be again the same term. Control C, Control V. Okay, let's try. There is something wrong here. Why? Because this might not exist there. What is the mistake? Okay, let me check. We say that M1, 2, this one should be I. Okay. And you see that we added this upper diagonal and the lower diagonal elements to the matrix. And let's check the sign. The sign is positive. Negative, 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 and this is positive. Then it's okay. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Therefore, now the created matrix size is 6 by 6. Therefore, this one should be -3. And let's check it one more time. This time 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We have created all elements on the main diagonal except then the last one. Therefore, I also, because I reduced the number of index to be 4. Therefore, I'm saying that when, let's say M N and let it be this one again. Control C, Control V, and H should be Hn because the last H is H3, and we have H3 at the denominator of this element. And we say that give MMN that now is 0. Okay, what is this? Give this to the last MN that currently is 0. And if I added this and press F5, you see that I created. This is the indeed -16 divided by 3H1. This is -16 divided by 3H2. And this is -16 divided by 3H3, as we have here. We created these elements, also these elements, and these elements, but there are another elements here and here. Therefore, we need to add another loop and update M more. I'm saying that, okay, let's find another loop. Let's change I from 1 up to length of x, let's say -4, n. Again, you see that this is either exist at the first, let's say when I is 1, it doesn't exist, but when I is 2, it exists, and when I is 3, again, it doesn't exist. We again use the same concept. We define S to be minus in the power of I, correct? And we say that if parameter S is -1, and if what? If M I and I plus 2, give what to the M and I plus 2? minus 1 over 3H2, yeah. Therefore, I'm saying that, okay, let's this time say that J is 1 again, and after that, give some, add some J, some 1 to the J for considering next element. Let's try if it or not. When I is -1, it means that we have only I is 1, I is 2. Therefore, we need to change the condition. When S is 1, it means that when I is 1, do nothing. When I is 2, it will be 2, 4. 2, 4 is the same. 2, 1, 2, 3, 4. This is 2, 4. Also, we have another terms for 1, 2, 3, 4, 4, 2. Also, 4, 2, where is it? Control C, Control V. Also, I plus 1, I plus 2, and I is the same, minus 1 over 3h h2. Therefore this one should be j plus 1, and also this one should be j plus 1. Let's just check if it's okay or not without changing out the size of the matrix. There is some error and it says length x. Where is it? Length x. Okay. And I want to look at the appearance of the matrix, and you see that we have created this negative element here but not here, and also created negative element. I created negative element here but not here and here. Therefore it seems that it's right, and the size of the matrix 1 2 3 4 5 1 2 3 4 5. The size of the matrix is okay. If I just want to increase the number of elements to be 4, to check it, if the M matrix appearance is again the same or no. And you see that when the I is even, we have this negative element here, not here, and negative element here, but not here. Also we have it here, not here, here, and not here. Therefore it seems this one also is okay. I reduce the number of elements to the 3, and let's continue further. Okay, let me just, I remove this x, we do not need it to see, we do not need the size of M anymore, we do not see x here, we do not see xm here. I'm just removing this extra element. I put a semicolon here to do not see xe, and what I see now is just M command window, and the M seems to be okay. What is the next? We need to create this right hand side matrix, and similarly you see that when I is odd we have 2he divided by 3, but when it is even it is he1 plus he2 divided by 6. Therefore here the right hand side matrix is 5 row, 1 2 3 4 5 row and 1 column. Therefore it's okay. The right hand side matrix is n minus 2 and 1, but we need to again add this element to this right hand side matrix by using S parameter. Again I am defining capital S to be minus, let's say minus 1 in the power of I. Okay, this is S. Now we say that if S is minus 1, it means that when the I index is odd, else n. When the index I is odd, right hand side matrix is what? It is 2h1 divided by 3. It is 2 times 2 hj divided by 3, and again I define j to be 1 here. Otherwise, Control C, Control V. Otherwise, when S is 1, it means that I is 2. The right hand side matrix here is h1 plus h2 divided by 6. Means that it is hi plus, or hj plus j plus 1 divided by 3. And here j is, when j is 1, it is h1, h2. When j is 2, it should be h2 and h3. h2 and h3, and it gives us this element. And after this, again, we added some 1 to the j plus 1. And I want to look at the right hand side matrix if it's okay or no. Do not need to look at matrix M, I remove it and let's press F5 and see. You see 1, 2, 3, 4, 5. All the term are the same because H1 and H2 is the same. Okay, let me just check it one more time. Everything is okay. We have 2H1 divided by 3, 2H1 divided by 3, and when I is even, it gives us the second element of this matrix, and second element is H1 plus H2 divided by 6. This one should be divided by 6. Now it's different. See, now it's different. This is the first, second, third, fourth, and fifth. Okay. Since this one is also true, let's define right hand side B. Control T. Okay, what is the right hand side B? Right hand side B, the size again is 5. 1, 2, 3, 4, 5 row and 1 column. Therefore, it is n minus 2 and 1. And we say that the first element is what? Minus 8 divided by 3HE. This is minus 8 times 2V left or V1 times 2V left or V1, because we define the left boundary condition here with V left. Yeah. Therefore, it is V left divided by 3H1. 3 times 2H1. Also, we need to define right hand side B. The second one also should be, the second one here should be 1 over 3 H1 divided by V left. Therefore, it should be 1 times to the V left divided by 3H1. H1, correct? Also, the end is minus 8 times to the V right divided by 3 times to H end. And we need to have another terms on the element before the last one, that is H and minus 1, and that one again is 1 times to the V right divided by 3H and or H and minus 1. This is H3, therefore both should be H and here should be H1, 1 divided by 3HN times to the V right. Everything is okay, and I enable the commands that we derived in the previous video. All is the same, and once we created right hand side, it should be multiplied by some f, because we have not considered this f coefficient in the right hand side matrix. This f coefficient times to the right hand side plus right hand side B. And this backslash means that calculate the inverse of matrix M and multiple to this inverse of matrix M to the f to the f times to the right hand side plus right hand side B. And because we calculated the central grid, it means that we have information of all grids at the center except on the left and the right boundary condition. The final numerical solution. In the final numerical solution, we should consider the left value of the potential and the right value of the potential at this Vn, and we give this calculated Vnc. We give this calculated Vnc to the Vn. Let's try if everything is okay. We might see a true solution. And you see, this is indeed the numerical solution when we have 3 elements. The first element, second element, and the third element. And this is indeed the middle, these are indeed the middle node, this one, and this one that we added to this, to the middle of this element to have more accurate calculation. And if you look, obviously, if we increase the number of elements, for example, when the number of elements is 30, the solution should be much more accurate. Therefore, I just remove this one to do not see anything in the command window. and just to see the numerical and analytical solution that are well coincide with each other. I think that's it. If you have enjoyed the video, do not forget to like it, subscribe the channel, and if you have any question, please ask in the comment, and if your question is a bit complicated, I will answer to this question in the Telegram channel that I mentioned at the beginning of the video. I'm just sweeping it down to show you every commands that I defined. Then you can easily reproduce the same code. And we wrote this code based on the previous one that we developed for let's say finite element method and linear shape function. Yeah, that's it. Thank you very much. See you later.